Okay, welcome everybody. So, in today's class, we are going to solve a problem. In the previous class, we have discussed about the basics of rapid and approximate analysis of building frames. So, mainly we saw while analyzing, we take the vertical and lateral loads separately. And we saw what is the condition for obtaining the maximum bending moment for a beam span, for a beam support, and for columns. Okay, so now let us discuss a problem. So the given problem is, in a multi-storied building, the frames shown in figure are spaced at 4-meter intervals. Dead load from the slab is 3 kilonewton per meter square and the live load is 5 kilonewton per meter square. Analyze the beam BC for midspan, positive bending moment. Self-weight of the beams may be ignored. Use two-cycle moment distribution approximation method. So, see, this is the given beam. This is the given frame. Okay, so it is a two-story, three-bay frame, and the frames are spaced 4 meters apart. It is given in the question that the frames are spaced at 4 meters interval and the dead load is 3 kilonewton per meter square and the live load is 5 kilonewton per meter square. So now you can see the beam span is 6 meter. We are asked to analyze the span BC. This span. Our aim is to analyze the span BC. So it is given that the frames are spaced 4 meter interval. So let us assume that half of the span of the slab on either side will travel the load to the beam. So in order to calculate the live load and the dead load, we assume that half the span of the slab on either side will transfer the load on the beam. So this is the beam BC and we know, so this may be the slab. So here at this side also we have the slab. So see, the frames are placed 4 meter apart, right? So half the span of the slab, that means from this slab about 2 meter, for a distance of 2 meter the load is transferred to this beam BC, and from this slab also about the load from about 2 meter will be transferred to the span BC. So the self-weight of the beam is ignored. So considering 1 meter length of the beam ABCD, you are considering 1 meter length, what we get is the dead load from the slab is 3, it is given. Dead load is given as 3 kilonewton per meter square. So 3 into 4, 1 into 4, we get 12 kilonewton per meter. Similarly, the live load from the slab is also 5 into 1 into 4. So it is 20 kilonewton meter. So 2 from one side of the slab and 2 from another side of the slab. So totally it is 4. Okay, now for maximum midspan positive moment in BC, we know the span BC has to carry dead load plus live load, while the spans AB and CD will carry dead load only. So we know, you see, we need to analyze BC. Therefore, BC should carry the live load also. So there are no alternate spans, only the nearby spans are available. So if we have a span DE, so this DE should also carry a live load. So now because we have only 3 spans, this span, that is throughout the beam ABCD there is dead load, and in the span BC we have only live loads. Okay, so how will we draw the substitute frame? So the substitute frame is like this. So ABCD, throughout the span ABCD we have dead load and we have live load only in the span BC. So we have calculated the dead load as 12 kilonewton per meter and we have calculated the live load as 20 kilonewton per meter. So in the span BC, the dead load plus live load, 12 is the dead load and 20 is the live load. So totally 32 kilonewton per meter. Okay, so this is how we will be drawing the substitute frame for the span ABCD for at this level, right? Now, so first step, because we are using the moment distribution method, so two cycle moment distribution method or approximation method, substitute frame method. So first step is finding the fixed end moments. So we have three spans, AB, BC and CD. So we know with for a beam with a fixed support and a UDL, our fixed end moment is equal to plus or minus WL square by 12. So first of all we are considering the span AB. So when we consider the span AB only has dead load. So we have a dead load of 12 kilonewton per meter. So what we get is, so the span length is 6 meter. AB span is 6 meter. So applying here we have the negative fixed end moment and at B we have the positive fixed end moment. So it is minus WL square by 12 and here it is plus WL square by 12. So we get calculating, we get minus 36 kilonewton meter and plus 36 kilonewton meter. Okay. So now similarly for the span BC also we have an UDL, but we have both dead load plus live load. So total of 32 kilonewton per meter UDL. So MFBC and MFCB is plus or minus. The left side, that is at B. This is B and this is C. So at B it is minus WL square by 12 and at C it is plus WL square by 12. So we get minus 96 kilonewton meter and plus 96 kilonewton meter. Now we have one more span, that is CD. Okay, so for span CD, we have only dead load in the span CD. So the left support, it is anti-clockwise, negative moment. So minus WL square by 12 and at the right hand side we have the positive moment WL square by 12. So we get minus 36 kilonewton meter and plus 36 kilonewton meter. So the second step is we need to find the distribution factors. So the calculation of relative stiffness we have already studied in our previous classes while studying the moment distribution method. Okay, now we assume the uniform moment of inertia. I is not given in the problem, so we will assume uniform moment of inertia throughout for all the members. And using symmetry you can obtain the moment distribution can be obtained because you can see the diagram once again. See, it is a symmetric, na? See, it is a symmetric. So only one half, analyzing one half of the span is enough so that you can obtain the analysis for the other half also. That will be similar to the first half. So we have two joints, we are analyzing two joints A, B. Only one half we are analyzing. So we are analyzing joints A and B. See, we are analyzing joints. We are analyzing joints A and B. Joints C and D will be similar to that of B and A. Okay, so we will stop with this. The remaining thing is similar to that of A and B. So first step we've calculated the fixed end moments. Second step is calculating the distribution factor. So we have two joints A and B. So in joint A we have three members. At joint A we have three members, that is A1. This is taken as A1 which will be clearly distributed in the next diagram. Okay. So at joint A we have three members A1, AB and AA2. Similarly, at B we have four members BB1, BA, BC and BB2. Okay, so we know the stiffness is when if the far end is fixed, if the far end is hinged, it is 4 EI by L. We have already studied it, this, right? 4 EI by, sorry, if the far end is far end is hinged, it is 3EI by L, and if the far end is fixed, it is 4EI by L. But now for the relative stiffness, we are not going to use this. We are assuming, see, there is the moment of inertia is not given in the problem. Therefore, let us assume that throughout the span we have uniform moment of inertia. Right? So finding the relative stiffness, we will find the stiffness. 1 minute. Okay. So see A1. A1 is the column, right? A1. A is like this. A. We have AB, A1 and A2. So everywhere it is fixed. All the intermediate supports we will assume as fixed supports. So for fixed support it is 4EI by L. Relative stiffness is 4EI by L. So while determining the relative stiffness, see 4EI by L. So everywhere it is 4EI by L. We will omit this 4EI because it is common for all the members, because everywhere I is constant, I is uniform throughout, E is also same, this 4 is also same. So this term becomes common for all. So it is enough to write the relative stiffness as 1 by L. Okay. So because therefore EI by L will get cancelled. Okay. So when we are taking relative stiffness, it is this AB, we know the span length is 6 meter, A1 is 4 meter and A2 is 4 meter. So relative stiffness is for A1 it is 1 by 4, for AB it is 1 by 6 and for A2 it is 1 by 4. So taking the summation 1 by 4 plus 1 by 6 plus 1 by 4 we get 2 by 3. Now for determining the distribution factors, this relative stiffness K, summation is sigma K. So distribution factor is K by sigma K. So what we get is 1 by 4 divided by 2 by 3. We get 0.375. Similarly for AB, the distribution factor is 1 by 6 divided by 2 by 3. So it is 0.25. And the distribution factor for A2 is 1 by 4 divided by 2 by 3, we get 0.375. Now we will take the joint B. So as we saw earlier, joint B has 4 members. Okay, so joint B we have 4 members. So joint B, here there is a C, here there is A. So we have B1 and B2. So this AB is a 6 meter span length, BC is a 6 meter span length, the column B1 is 4 meter and B2 is 4 meter. So what we get is 1 by 6. For BA, the relative stiffness is 1 by 6. For B1, the relative stiffness is 1 by 4. For BC, the relative stiffness is 1 by 6 and for B2, the relative stiffness is 1 by 4. So taking the summation of all, we get it is 5 by 6. So the distribution factor is for BA, it is 1 by 6 divided by 5 by 6, we get 0.2. For B1, we get 0.3. For BC, we get 0.2 and for B2, we get 0.3. Similarly, you can continue for the other cases also. That is, if you are taking C and D, it is similar to that of A and B. Okay, joint C will be similar to joint B and joint D will be similar to joint A. Now, we will draw the moment distribution table. So here it is 2-cycle moment distribution table for the substitute frame. And see, while writing the moment distribution table, here we are taking the vertical loads and the horizontal loads separately. This substitute frame method is a method to analyze the vertical loads. And here our aim is to analyze the beam or the span BC. So it is enough to take the beams. we do not take the columns, we are taking only the beams. So at A, so it is like this, right? A, B, C, C and D. So at A, we have only the span AB, right? At B, we have the span BA and BC. We are not considering the columns, only the beams. So BA and BC. At C, we have CB and CD. So these are the distribution factors for AB. Distribution factor is 0.25. We have calculated here. 0.25. Distribution factor for AB is 0.25. These columns we are not considering. So distribution factor for BA is 0.2, for BC it is 0.2. So at a joint C it is similar to joint B, right? So for CB and CD it is 0.2 and 0.2. Now let us write the fixed end moments. So we have already calculated the fixed end moments in our first step. So for AB the fixed end moment is minus 36 kilonewton meter. For BA, the fixed end moment is 36 kilonewton meter. That is minus plus. And in BC, in the span BC, for BC it is minus. So minus 96 kilonewton meter. And for CB it is 96 kilonewton meter. And CD it goes on like that. Okay. And if you need, you can calculate D also. So for D, you will have the span DC. For the distribution factor will be similar to AB. So it is 0.25. And for DC, if for CD it is minus 36, so you will have plus 36. Right? So if it is needed, you can calculate so on. Now, after writing the distribution factor, we wrote this fixed end moment also. Now we need to balance it. After writing the fixed end moments, we need to balance these end moments. So balancing is this fixed end moment, summation of the fixed end moment into distribution factor. So here it is minus 36 into 0.25. So while balancing, you will be giving the opposite sign. If it is minus 36, you will be giving plus. So it is plus 9. In BA, at joint B, see, take the summation of 36 and minus 96. So 36 minus 96, it will be minus 60. So minus 60 into 0.2, you get minus 12. So balancing, we will be taking the opposite sign. So plus 12. Similarly, for BC, also the distribution factor is the same. So it is plus 12, right? At the joint C, 96 minus 36. So it is plus 60 into 0.2, we get plus 12. So for balancing, we will take the opposite sign. So it is minus 12. So minus 12, minus 12. Next is the carryover, right? So see, 2 times we have to do the balance. With that, our iteration will be stopped. So when you are carrying over, your carryover will be between AB. So from AB, between AB, from this to this and from this to this, because A is fixed support, from this half of the load will be carried to the fixed support. If it is simple support or hinged support, this will not be carried. Okay, that all is clear for you. Well, we have discussed it in detail while studying the moment distribution method. See, now we are not distributing this. We are not taking the half of this. If needed, you can take here it will be plus 6. But we are not considering this because our aim is to analyze BC, to analyze the span BC. Okay, so I have omitted this. Now, so from this AB, half will be transferred to BA. So 9, half of 9 is 4.5. Then next transfer is in span BC. So from BC to CB and CB to BC. So here from this 12, half will be transferred to CB, that is plus 6. And from this minus 12, half will be transferred to BC, that is minus 6. Okay. So now see CD, that is not in our consideration. So I am just omitting that part. So now we will balance it. So balancing, here it is at the joint B. See, balancing has to be done in the joints. So at the joint B, we have two moments now. Carryover is nothing but the moments. So we have 4.5 minus 6. So add these both moments and multiply by the distribution factor into 2. So this is negative minus 1.5. So balancing, you will take the opposite sign, that is plus 1.5. Similarly for BC also, 4.5 minus 6 into zero point 0.2, we get plus 1.5. So it is minus, adding everything, that is, see, don't add the distribution factor from the fixed end moment. So adding minus 96 plus 12 minus 6 plus 1.5, you get minus 88.5. So this is your final moment at joint B. In the span BC at joint B, your moment is minus 88.5 kilonewton meter. Similarly, at joint C, for the span BC, your moment is this 96 minus 12 plus 6 minus 1.5, it is plus 88.5 kilonewton meter. So we are in our question, we are asked to analyze only the span BC. So we will stop with this. We are not caring about the other parts. So now we have obtained the final end moments, final moments. Now we will draw the free body diagram. And see, while studying the moment distribution method, the summation of all the moments at the joint should be equal to 0. We have studied that. But here it will not be equal to 0 because we are not considering the column. That is the sum of moments at joint B or at joint C. If you take the columns, the moment distributed to the columns, are we are not considering that. Okay, so that the summation will not be equal to 0. Now we will draw the final bending moment diagram. So for the span BC, we will take the span BC. Okay, so this is our span BC. Okay, so we know for the span BC, total load is 32 kilonewton meter. That is live load plus dead load. Both addition of both live load plus dead load is 32 kilonewton per meter. And now we have obtained the moment as minus 88.5. Minus 88.5 and plus 88.5 for BC and CB. So for BC at this end, it is minus, that is anti-clockwise, 88.5 kilonewton meter, and at this at C, joint C, it is clockwise, that is 88.5 positive, 88.5 kilonewton meter. Here it is minus, so it is anti-clockwise. Okay, now we will draw the bending moment diagram for this condition. For these loads and moments, we will draw the bending moment diagram. So while drawing the bending moment diagram, we know it is a combination of both. First of all, we have to draw the free bending moment diagram or simple bending moment diagram by considering the ends as simple supports. Okay, so while considering the ends as simple supports, we know the free moment at the center of BC. At the center of BC, our moment will be equal to WL square by 8. Okay, so it is WL square by 8. So I will write here So free moment at the center of BC is equal to WL square by 8. So that is 32 into 6 square divided by 8. We will get 144 kilonewton meter. Okay. So now, see, you consider the joint B and C. While considering the joint B and C, here we have the negative bending moment. So while we are drawing this anti-clockwise or negative moment, it will point towards the top, right? So this is negative. So at the support we have 88.5 kilonewton meter. Here it is positive, right? So this is also pointing towards the up. So here we have right clockwise. So it is 88.5 kilonewton meter. Right? So how the bending moment will be? Near the supports there will be hogging, and in the center of the span there will be sagging. So here because of this load, or because of this load, your bending moment diagram will be like this. And at the center you will have the maximum, right? So here it is negative and here it is positive, sagging and hogging. Okay. Now the design moment at the midspan. See, at the midspan, what will be your design moment? So design moment at midspan will be equal to, so at the midspan, the free, that is, if the beam is having simple supports, our bending moment is 144, and because of the fixed support, the bending moment gets reduced by 88.5. So how much we get? 144 minus 88.5, we get 55.5. 55.5 kilonewton meter. See, that means this distance. No? See, this distance. This much is 55.5. 55.5 kilonewton meter. So we'll mark it here. So this is 55.5 kilonewton meter. Okay. And the total is, we know 144, right? So this total. So So 55.5 plus 88.5. So total you get 144 kilonewton meter at the center of the span. So this positive and this negative gets compensated, right? So at the supports our positive and negative bending moments are, or negative and positive bending moments are 88, sorry, at the supports the negative bending moments are 88.5 kilonewton meter, because we know while we are taking the bending, the right clockwise and left anti-clockwise is negative, right? So that is why the left anti-clockwise is negative and the right clockwise is negative. So at the supports we have negative bending moments, and at the midspan we have the positive bending moment, right? So that's all. Therefore, see, we are asked to find the midspan positive bending moment, right? Therefore, the answer is midspan positive bending moment in the span BC is equal to 55.5 kilonewton meter. That's all. Okay. So, I will explain you once again if needed. So we are given a frame which is spaced 4 meter apart. The beams are of spans 12 kilonewton meter and the column is 4 meter. First of all, we have to determine the substitute frame, find the dead load and the live load, draw the substitute frame, mark the loading conditions, find the fixed end moment, determine the distribution factors, then determine using the 2-cycle moment distribution method, determine the final end moments. Then you can draw the bending moment diagram and you can find the final positive midspan bending moment. So that's all. So thank you for today. We will see the next problem in the next class.